Hello, everyone, and welcome to another episode of PyTorch Community Voices. I am Suraj. I am a developer advocate at Facebook AI, and I'm also your host today. Um, as some of you have been with us before, this show follows the format where people from the PyTorch community come in and talk about their projects, and the audience has a great chance to interact with them in real time. uh, Today I have the privilege of hosting two very special guests, William Falcon and Thomas Chaton from PyTorch Lightning. Hey Thomas, hey Will.
Hey, hi.
Hey, thanks for having us.
Can you give us a brief introduction of yourselves?
Yeah, so I'm William. I'm the creator of PyTorch Lightning.
Yeah, I'm Thomas. I'm a research engineering manager at PyTorch Lightning, and I've been on the project for 10 months now.
So Tomal leads a lot of the Lightning work right now. So you'll interact with him, on Slack and GitHub all the time.
Great. Cool. So what we have today is a bunch of slides that Thomas is going to walk us through. And then we have an interactive coding session where honestly, I don't know what we're going to be doing. So I'm waiting to find out myself. Thomas, do you want to take it away?
Yeah, definitely. Okay, so let me quickly share my screen. Cool. Okay, so can you see the slides?
Can see your notes. So you have to switch the presentation. Yeah.
Wrong one. Sorry for that. Always happen. Okay, so tag. Okay, can everyone see my screen now?
Yes.
Yes.
Okay, awesome. So here are some slides to basically present Lightning. So that's from William and me. So we will talk about PyTorch Lightning and the Lightning API. We will talk about some Lightning features, and then we will move to the demo, which is PyTorch to Lightning and how to make that transition. So first, why Lightning? So as a researcher, you want to iterate on research quickly, but most of the time, like you spend a lot of time working on deep learning engineering and not the research, which is actually what matters. And it's why we came up with the Lightning API, which is a way for us to, and for you to organize your code in a simple component, make it readable and reproducible, so you can really focus on what matters, the research. So we have a Lightning module, we have a Lightning data module, we have a trainer callbacks, we have the torch metric library, we have Lightning accelerators, and the first component is the Lightning module. So what it does is encapsulate all the research code. So it improves readability, and the way to use it is by implementing some of the hooks. So you can override the training step and basically put all your training related logic inside of that function, and then optionally you can implement a validation step, test step, and predict step. You can also override the config optimizers to define your optimizers and scheduler. So here we have a lift model which takes an N module. In that case, it will be like a ResNet 50, which has been pre-trained and coming from PyTorch, from Torch Video, and that's basically how we lift a model using Lightning. So pretty easy to convert from pure PyTorch in this case. Then we have the Lightning data module. So that's basically the equivalent to the Lightning module, but for the datas. So really organizing the data loaders. So here we have multiple hooks: train data loaders, val data loaders, test data loaders, and predict data loaders. You just need to return the data loader you want with the data associated to each one of the stage. So once you have implemented those two components, your code has been is fully encapsulated. It's much more readable, and it's really like a standardized API. Every time you go onto like a new Lightning repo, it's you know where the code is, which is pretty amazing to get through. So once you have those two components, the module and the data module, you can create the trainer. So the trainer is really the component which really reduce all the boilerplates around the optimization and distributed training and logging and many more. So what you do is you create a trainer, and then you provide to the trainer.feed function the module and the data module, or the module and the data loaders. You can also call trainer.validate if you want to validate, test, and predict. So predict is really used also for prediction, like scaling the prediction. The next component are callbacks. So callbacks are self-contained components, self-contained programs, in which you can customize your Lightning code. So it's fully encapsulated. Okay, actually, jump a slide. And you can override any of those hooks to customize Lightning to your needs. So in each one of those hooks, you will get the trainer, you will get the PL module, and from that, you can basically access all the Lightning ecosystem and modify the code to your needs.
Yeah, and I think it's important to kind of explain what a callback is at a high level, because it's if you're just starting out in software engineering, maybe it's confusing. But if you think about the program as like a line, like you from start to finish, and you want to kind of hook into different parts of that, right? Then you can do that through one of these callbacks, right? Where you can say, okay, look, here's a collection of hooks that are going to be called along the path of that program. And then when that happens, it's going to do something. And that's going to be self-contained in this callback. You can have many callbacks, right? This one happens to print like some metrics along the way, just literally printing them out. But you can do it like when training starts, when training ends, and there are like dozens of these hooks that you can plug into. But this is a concept that comes, all the way from web development, from mobile development, right? Introduced in the 1980s, 90s. So it's kind of been brought into the AI world, and this is kind of the Lightning version of that.
Yeah, exactly. And here we have like a very simple example, like a print table metric callbacks. Let's say like as a user, you want to print your metrics within a table at the end of the epoch. You just override the on epoch end hook. You access the metric through the trainer, and then you just print them on rank 0. And if you want to use that new callback you just implemented, you provide it to the trainer callback arguments alongside all the other callbacks you want. So here, GPU stat monitor, early stopping, and many more. The next part I wanted to introduce is the PyTorch metric library. So it's a library which implements 25 plus metrics which are rigorously tested and which can be used with Lightning or with pure PyTorch. And one of the great things around metrics is it performs accumulations and reduction automatically across multiple batches and within distributed settings. So when you train with multiple DPUs, you don't even need to care about the synchronization to be done. Like metric will do it automatically for you. And the way it works is the following. So if you want to implement your own metric, you just import Torch metric. Here is an example for implementing an accuracy. So the way is you register some state. So here I'm going to register correct and total. I'm going to implement the update function. So here I'm going to increment correct by the number of correct prediction I have made. And I'm going to increment total by the batch size. And then on compute, I'm going to return the ratio between correct and total. And as I said, if you work in the distributed settings, correct and total are going to be reduced before compute gets called across processes. So you actually get the correct metric.
Yeah, and I think I want to. Can you go back to it for a second? Because if you haven't done distributed training, or if you're like starting to and you're implementing your own, it's really easy to get started. With like the examples. They're like here, drop this thing in distributed data parallel, and it's like one line, and you're like magically there. Yeah, that's true to like get started at a very basic level. But when you actually try to do it, in like anything meaningful, you're going to run into a ton of issues around synchronization and like who does what model, like what GPU and so on. And so these metrics, if you're using Lightning, you don't have to deal with it, right? You're just using Lightning, and like Lightning it's like you're coding for one GPU, but you're going to work on, 1,000 GPUs, doesn't matter. But if you're not using Lightning and you still want to get the metrics out of it, you can use this, and then it will use like a lot of that Lightning magic under the hood to do the distribution for you, which is cool because like, it's not easy. Like I want to emphasize this. It's like, how do you, for example, accuracy is an easy one because yes, it's splittable. You can like average each GPU and then average the averages, that kind of thing. But like other metrics don't work like that, right? So it gets pretty hairy, very complicated, very quickly.
Yeah, definitely. And one great pointer on metrics is they are extremely well tested, which means when we use it for benchmarking or to actually report your benchmarks within your papers, you can be pretty sure that those are the correct numbers. Okay, and the next part I wanted to talk about is the Lightning accelerators. So that's really like the muscles of Lightning, how we do like the distributed training. And the way it works is we have the trainer and the loops, and the loops communicate through the trainer with the accelerators. The accelerators support CPU, GPU, TPUs, and IPUs. And then accelerators have subcomponents, which are precision plugins and training type plugins. Precision plugin takes care of how the tensors should be stored. So FP32, do you want to do mixed precision, or do you want to do precision 16 on TPUs? And then you have the training type plugins, which really handles like the distributed training. So like training on one device, like doing multiple device with one process, doing like one process per device. So basically DP, DDP, DDP2, and then you have all the other frameworks which are there to actually scale the training. So like deep speed, fully sharded, DDP sharded, and so on. And overall too. And then you have also the cluster environment, which are the way for Lightning to automatically pick up what cluster you are running on, and making sure that if you are using Slurm, Torch Elastic, and many more clusters, like everything works out of the box. So
yeah, and this this accelerator thing is like Tomas said, it's at the heart of Lightning, and it's been there from the very beginning, right? I think in the beginning it was not directly called accelerators. That was renamed about last summer, roughly, and then this API was brought out. But this is extremely powerful, and we're just starting to surface a lot of these functionalities to users as well. But what's interesting here, it's like the combination, right? Like the fact that you can do GPU or TPU or IPU with FT32 or AMP or FP, and like if you just multiply all these, right, it's like 4 to the 4 combinations of things you could do here, right? So I think what makes Lightning unique is the ability to test everything. Like we test all of these combinations, and all of it works together. And so like it's just, yeah, it's a lot of work on our end, but it makes the PyTorch job a lot easier.
Yeah, definitely. And we went through that refactor. So actually the accelerator API right now, it's like the third iteration of the API design for accelerators. And the new paradigm with like the training types enabled us to actually go pretty quickly and integrating like new backends. So like deep speed 0 from 1 to 3 from Microsoft was quickly integrated, fully sharded. We just added also TPU pod support, so you can really like scale your training with Lightning on TPUs. And all this API really enabled us to go very quickly. So.
Yeah, and I want to call out the TPU effort, because I mean that's been a lot of work on the XLA team on the PyTorch side. And we work closer together with the team, but that's been just, I just want to recognize that it's been years of effort on their end to make that happen holistically for everyone, not just us. We've surfaced it in a way that's really easy for you guys to use. So, and just the Facebook and Google teams have done a lot of effort here as well.
Yeah, definitely. Okay, so moving to some of the state of the training features you get out of the box with Lightning. So the most obvious one is really distributed training. So if you want to train on one GPU, what you need to do is basically putting GPU equal 1 within your trainer. Let's say you have 8 GPUs available, you just do GPUs equal 8. Now you want to scale up and you want to train on 256 GPUs out of 32 nodes. You just put GPU equal 8 and num nodes equal 32. So no code change. It's really like just one line. You change those numbers and it just works out of the box. And one thing which is really amazing here is all the plugins you get directly through Lightning and through this accelerator API. So like if you want to train with deep speed or DDP2 or overall or DP spawn or all of those, that's basically just a string to change within your trainer, and we just handle all the back and make sure everything works properly. Lightning also comes with an automated version checkpointing, so we basically keep track that everything works, and it also works in distributed settings. We have built-in support for all the most common loggers, so TensorBoard, 1DB, Comet, MFlow, Neptunes, and many more. We have also a way for you to find bottlenecks within your code. So we have multiple profilers at different levels, so from simple, advanced, and PyTorch. And we recently added also the XLA profiler, so you can actually investigate your model performances on TPUs. And I think the core fundament of Lightning is we want that code to be working extremely well. So it's very well tested. So we test across multiple operating systems, across multiple Python and PyTorch versions. And we test on CPU, multiple GPUs, TPUs, multi-node, multi-GPUs, and we recently added CI for IPUs. So when you use Lightning, or when you do your research with Lightning, you can be pretty sure that all the parts we automate are extremely well tested, and you can be really confident to actually move your research to production, because Lightning really right now is getting extremely strong in the part that it actually automates.
Yeah, and I want to add as well, we benchmark against the equivalent PyTorch models for speed and accuracy, and like make sure that we get exact same solutions, right? So on every single pull request on CI/CD, we'll take a few different types of models, RNNs, CNNs, that kind of stuff, and we'll do the PyTorch version and then the Lightning converted version of it. And then we ensure that they get the exact same results in the same exact time.
Yeah. And then you definitely get many more features, accumulated gradient, all this logic on debugging, early stopping, JIT export, memory profilers, Onyx export, truncated backpropagation, quantization, stochastic rate averaging, pruning, prediction, and many more. And all of those are listed through our docs, so you can definitely learn more there. So now I'm going to switch to the demo, and if people have any question, they can interact directly within the chat. So
yeah, can I jump in real quick just to kind of motivate while you set up the demo?
Yes.
I think I want to make sure people know kind of the background of this, right? Because I think we all go through this iteration, right? So, remember Lightning really was born out of research, right? So it's born out of a lot of the work that I was doing probably since, I don't know, 2016, 2017, during my undergrad, many years of iteration, and then eventually open source during my PhD, and then really scaled up at Facebook, right? So when I was at Facebook AI Research, a lot of this stuff was built internally as well to be able to scale up on the Facebook clusters and so on. But the whole point there is that this was really built around being able to be iterative and fast, right? So I had spent years using many other frameworks, right? And tried all of them and published papers on all of them or built stuff with them. So they're all great for their specific purposes, but I really wanted to make sure that as someone who, iterates a lot of models, that you could go between idea and idea very, very fast without having to do a lot of boilerplate, right? And have that scalability and flexibility, which I think other frameworks kind of miss at that moment, right? And so that was at the core of it. And it's been like a year and a half or 2 years after that, and a lot of it has now been focused on production as well, right? So I think we spent like the first year really nailing the research side of it, and now it's been used across production, and thousands of companies across the world, major tech companies, right, use Lightning for training and deploying things at scale. So it's very well stress tested. I guarantee you will not exceed their scalability. But yeah.
That's a really good point. In fact, when Thomas was presenting, the one thing that was so obvious to me was just how clean the code was. That's the main thing that attracted me and many others to PyTorch, by how Pythonic the API is, by how neat your code is, and PyTorch Lightning just takes that to another level. But I do have a question for you. When you were designing the API, a lot of different libraries try to do this, try to make it easier to and write less boilerplate, but they run the risk of becoming opinionated. They run the risk of kind of dictating to the user how things should be done. How did both of you bridge this gap and find that sweet spot?
Yeah, so we have strong values actually that we set up from the very beginning of the project, but I will say it wasn't easy. I think like we're still in this process, right? And we try a lot, and we make mistakes, and we'll fix them very quickly. But it was probably like 3 or 4 years of actual research of like trying things out, right? Like my first iteration of Lightning basically looked like sklearn, right? It was like you take the model and you put the fit inside the model class, and then you call that fit on that, and it was bad basically. But I didn't know that for like a year and a half of messing around with it, right? And then eventually I realized you could move things around and shuffle things, and over many iterations, eventually it ended up being that like, hey, it's actually better to do it this way or that way. And actually, a lot of people at Facebook helped me kind of get to those final design decisions, like a lot of the PyTorch people as well. So it wasn't, I mean, it wasn't really just me, it's a whole community as well. So we've had a lot of help. But honestly, it's just been a research project for so many years in terms of like, if you think about like AI as a field it's evolving, and like a software engineering practice, you know, software engineers have had many years to figure things out, right? Like if you code Node or React, there are like standards, right? And like, you know how to do that, and you know how to structure JavaScript, and you know, the way you build projects or whatever. That doesn't exist for AI today. So a lot of what we've been doing is like, hey, this thing came around, it's called deep learning. Well, how should code be structured? How should things interact with each other? Like what belongs in separate classes? Is it the model or the data, the transforms? Which one is it? How do they interact, right? What if you need to collaborate with your team? So I think we've been doing a lot of that work on like, okay, let's figure out how to make things reusable and structurable. Whereas I think that the frameworks that came before, what they were focused on was, let's build a neural network, layer 1, layer 2, layer 3, here it is, right? And that was good in the beginning of like the deep learning thing, because that's all we needed to do. But then models got really complex and systems started interacting together, and you had many models like GANs and transformers and so on that were not just a single neural network, but they're collections of neural networks working together. So it was clear that there was this missing abstraction of like, okay, how do they play together? And that's really what Lightning is.
One of the values that PyTorch adopted when they were designing their API was to keep people who design the neural networks or build the neural networks first. And they really optimized for the research process. What values does PyTorch Lightning hold very dear to you know, the library?
Yeah, I'll call one out, but then Tomas can call out the other ones. So I think the main one is, we do the hard work, not the user, right? Like I think that's the core of it. It's, you know, you see that one line that says GPU equals 8 and num nodes equals 32. That's like 10 characters for you. That's like a year and a half of work for us, right?
Well said.
Okay, I guess I can go to the demo.
Before we head there, Thomas,
Yeah.
For all our viewers who are joining us now, we have Thomas and William from PyTorch Lightning. We just went through a really awesome deck where they showed us a really comprehensive introduction to PyTorch Lightning. And we will have more questions after this as well. But before that, Thomas is going to walk us through an interactive code demo. And the keyword being here is interactive. So if you have any questions for him while he is coding, please put that in the chat, and I'll find a way to pipeline that to Thomas.
Yeah, thanks a lot. Okay, so I'm going to share again my screen.
Can people follow along? Or I don't know, like, can they clone the repo and do it themselves as we do it, or is this?
Yeah, I think they can. So okay, so I created this repo here under my username, so Chaton, and the repo name is called PyTorch Lightning. So if anyone wants to actually get there, clone the repo, that's entirely fine, and we can follow the steps all together. So here's what I try to do with that repo here. So I'm going to try to explain to the community how to convert pure PyTorch to Lightning. So I took the simple example out there from PyTorch, which is training a CNN on Minst. And then I started to add more features. So basically trying to add a distributed training, a commuted gradient, profiling to pure PyTorch, and showing what's the equivalent within Lightning. And then I will quickly talk about grid and talk about Lightning Flash. So awesome. Here are the piece of code, right? So I'm going to run everyone through the code. So here I'm giving all the credit to the PyTorch team to implementing these great examples. which is basically training a very simple CNN on means, right? So first of all, here we have an argument parser, which is going to get the batch size, the number of epochs, like some arguments we need to run our script. We are going to check if we have some GPUs available. We are going to create the device on CUDA or on CPU, depending if we have some GPUs. We are going to here create some cargs, so like some arguments for the data loaders, so the batch size, the number of workers. Do we want to pin the memory? If we use GPUs to accelerate training, do we want to shuffle the training data? Here is the implementation of the transform. So the means data are actually NumPy arrays, so we are going to first convert those to tensors, and then we are going to normalize them. Here
Thomas,
we are. Yes.
I hate to interrupt you, but would you be able to zoom in a bit?
Yes, definitely. Yeah. Is it better?
Yes.
Awesome.
Can you do one more? Just a little more.
Yeah, definitely.
There you go. Nice.
Perfect.
Perfect.
Okay, so the next step is relying on Torch Vision. So Torch Vision provides lots of pre-built data set, means CIFAR10, ImageNet, and so on. So here we are just going to create two data sets from means, one with true equal true. I'm going here to force the download of the data. Here true equal false for my test data set. Provide the transforms, and then I'm going to instantiate my data loader. So data loader take a data set and all the cargs which are defined before, like the batch size, the number of workers, and so on. So now my data are being handled in pure PyTorch. So the next step is, yes.
They're asking for one more zoom, I believe. Nice. Look at that.
Perfect. Awesome. So the next phase is really creating the model, right? So here I create my model, and then I move it to the device. And just as a reminder, the device is basically a Torch device as a CUDA or CPU, depending if we have GPUs available. Then I'm going to create my optimizer. I'm going to create my scheduler, and I'm going to iterate manually through my loops. So I have a train loop and a test loop right here. So I'm going to quickly show how those loops. So I get the models, the device, the data loader, the optimizer, and the epoch. I'm going to iterate through the data loader. So I'm going to get a batch of the data every time. I'm going to move the data to the devices and zero grad the optimizer. So just making sure that we don't have any gradients on the model. Forward the model through the data through the model. So the model is basically a series of convolutional neural network with a last layer, which is a linear layer. And basically the value 10 here is because we are performing classification on means, and means as 10 digits. And the output of our series of convolution and fully connected layers is basically a log softmax, which I can then pass to the computation of my loss. So I can provide this output here, and my target, compute my loss, perform my backward, and perform my optimizer step. So that's most of the training loop. And then on the test loop, I need to make sure that I deactivate my gradients to get slightly faster, that I need to put my model in eval mode, and here to put my model in train mode. And here, same as before, I'm going to iterate from a train data loader, move the data to the device, compute my accuracy, and print my accuracy. So that's really like the PyTorch example. And then I will implement that example here with Lightning. So
wait, sorry, can you zoom in again? Yeah. And
yes.
I think everyone here probably already knows that example, so that's good.
Yeah.
Like you guys, that's just plain PyTorch. Nothing magic happened here.
Yeah, exactly. And then I will add more features to the pure PyTorch to show like how things get scaled.
Yeah.
So,
and then just one more because it's still a little bit small.
Yes, definitely. Okay, cool. So here we have this new component from the Lightning family, which is a Lightning client. It takes a Lightning module and a Lightning data modules, potentially some trainer defaults, cargs, and callbacks, and that's just going to be a way for us to interact directly with our script. The same, it's basically replace all this argparse code we had previously. And from that, we can call basically the feed function, the test function, and so on. So here we can see that all this code right there has been basically entirely replaced by just 4 lines of codes. So now where everything goes, right? So we have the first component, which is a Lightning model, right? So let's quickly look at that. So here was how we created the model. So when you use Lightning, you can actually like lift the model. So here we basically get like a model, potentially some extra arguments. You can call this helper function, which is called like save hyperparameters. That's going to just save all those extra cargs, so you can reuse them when you load the checkpoints. So those will be saved with the checkpoint, and you can reuse them later. We create our model, and we create a collection of metrics. So those metrics are using a torch metric accuracy implementation and the metric collection. So here I create a train accuracy metric and a test accuracy metric.
Yeah, and there you're passing the model in, right? So
yeah,
I think we use the word model a lot in the machine learning world, but it's kind of abuse. In this case, you're passing in an actual model to a Lightning module. Yes. Could itself be a model, but in this case, it's just a single model, and then you're going to do something on the model. If it's like an autoencoder, you would pass like the encoder or decoder, or you could initialize it within here as well.
Yeah, exactly, and that's what we call in the Lightning vocabulary, like lifting a model. So here we are basically providing this exact same neural network, but it could be like a ResNet 50. It could be like any CNNs basically that fit the requirements of the number of classes and the loss computation. So it's basically you just add your component, your Lightning module, which takes whatever you require. So let's say you train a GAN, it takes like a generator discriminator. If you train whichever models, and you just lift the model to actually use Lightning as your training engine or prediction engine. So the second part is really trying to move the loop code, right? So that's something that the community took some time to get through, but I think that was one of the primary contributions that actually made Lightning different from the rest. So basically all the code here, all the code you see here actually within the train loop actually gets moved out to the training step, right? And here, because the training step and test step are extremely similar, I implemented this shared step. So here first, we basically get our batch, and that's just 2 lines of code here. So here we can see that previously in PyTorch, we had to move manually the data to the device, but Lightning basically takes care of that. Then we forward the data through the module, we perform the computation, and one extra component here is, here we were basically doing all this extra logic to log things, right? And here we had this logic to get basically the predictions and compute the accuracy and perform the predictions. So here we can see like we increment the number of corrects, and then we basically get like the final accuracy on the training. On Lightning side, it's quite simpler because now I can basically just do like self.log, log my loss, potentially on the progress bar and the logger by providing progress bar equal true, logger equal true, and more arguments are also available. And then you can do also self.log, name your accuracy, and actually access from the metric collection the accuracy that you require, and that will be logged alongside. So that can be used for training step and test step. And the last part is actually the creation of the optimizer and scheduler. So that actually lives right here under this configure optimizer hook. So here you create your optimizer, your scheduler, and if you don't have any scheduler, you just return your optimizer. If you have optimizer and schedulers, and you can have multiple of them if you want to train GANs, for example, you just return a list of optimizer and a list of scheduler. If you wanted to have, for example, so here we can see that schedulers are actually being stepped on epoch. In Lightning, if you want to adapt your schedulers on epoch or on step, you can just change that to actually dictionary and say interval equals step, and that will call your scheduler on step. Yeah,
and just to clarify here, that method shared step, that's something that he created for this particular script, right? It's not part of the Lightning module. This just happens to be like an intermediate code. So the actual required functions are training step, configure optimizers, and inits, right? That's it. Yeah. Then if you want a test loop or validation tube, you can add these. But if they're all 3 the same, then we usually just come up with a kind of middle function that we just call, I call it step sometimes, he calls it shared step, people call it whatever.
Yeah, exactly. And I think it really depends on your model. Like this one is really simple, so it makes sense to have like a common step. But sometimes you have like really complex model with like very complex training strategy. So you can't really do that because training is really different from the rest. So most of the time, validation step and test step shares on the same code. One thing which actually I didn't talk about was all the optimization part. So here we can see that we had to manually call loss.backward, zero grad the optimizer, call optimizer.step. But here in Lightning, it's actually much simpler. Like you just return the loss, and Lightning takes care of doing all the optimizations, potentially in the distributed settings with different precisions. So it's really, you get the data which are already on the device, forward them through your module, return the loss, and it just works, right? That's what Lightning provides at a very high level.
Yeah, and there are some, some PyTorch purists will want to do it themselves, right? They want to do the backward or whatever else. You don't lose that flexibility, right? Here, this is called automatic optimization. And you can enable something in Lightning called manual optimization, where you can just call it yourself, like you would in PyTorch, and you still get all the benefits of the other stuff.
Yeah, exactly. It's basically you just, on your Lightning module, you set automatic optimization equal false, and then you have a couple of functions you can use. So you receive, you basically get your optimizers. You just do like set.optimizers, you receive your optimizers, and then you can use a set.manual backward function, and we implement everything you want. So basically the only thing which is going to change compared to that code that you manually do is instead of calling cell.loss.backward, you call cell.manual backward. And we do that so we can actually enable gradient accumulation when you run with distributed training. So the second part is organizing the data. So going back to the PyTorch code, we had all this piece of code right here, which is a bit hard to follow. We have cargs, we have those conditions here. It's a bit hard to follow, I would say. So here we have its counterpart, the Lightning data module. So here I'm basically getting all those arguments, all those cargs are expressed within my init functions. I also have a description for each one of them, so it's easier to read and explore the code. I have the creation of my transforms. And then we can see that the data loaders have been organized behind, sorry for that, I have a dog making some noise outside.
I think your dog's trying to code, so it's like, you have a bug.
So here I have the train data loader. So I just create my means data set, return my data loader, test data loader, and we have the same for validation and predict. So once you are there, you can basically call your client, and that's going to auto-generate all the configs, and you can really do everything from the command line. Then trainer.fit, test, and save your arguments. I'm going to quickly run that so everyone actually sees it on the Lightning side. So the way it works is you can just take that code, run it, and if...
Can you zoom in on this one too?
Yeah, okay, awesome. Why is it breaking? Did I change anything?
Yeah, and by the way, this data module, like, it might seem weird at first. Again, you can use data loaders directly if you want, but if you ever had this issue where you're working with people and you're like, wait, what transforms did you use? Like, how did you schedule this? How did you split things? All of that can be answered by just having a data module. Then you say, here, just use it. And then you know exactly you're using the same data as anyone else.
Yeah. So here I'm running the first script. So here we actually see the losses going down, which is what we will expect.
And this is a PyTorch one now?
Yes, exactly. And here I'm going to run Lightning. Something was breaking. I hope it's, okay, perfect, it's working. So here I'm actually running on a machine with 8 TPUs, just in case we want to actually show some distributed training. Okay, so this one is going to start. While it starts, I'm going to go to the next part. Okay, so I'm just going to unzoom a bit on this one because we can't see anymore anything. So, okay, so the next part, and I'm going to quickly show the high-level thing. So we are going to add DDP support to the PyTorch pure examples, and we are going to add DDP spawn, accumulated gradient support, and profiling. And we are going to show how that looks on the PyTorch side and how that looks on the Lightning side. So here's how you do distributed training with pure PyTorch. So let's go back to the code. So compared to before, there's a couple of things which are going to change. So the first one is when you want to train in a distributed setting, you actually need to set up DDP. So the way it works is you're going to get a local rank and a work size, and you are going to init a progress group. And the progress group is going to be a way for the different processes to communicate with each other. There is one extra thing here. So when you train with multiple processes, you need to use a distributed sampler. And the distributed sampler is aware of the rank, so like the rank of the process, and is going to chunk the data accordingly. So each process is going to handle and train only on a sub section of the data. One extra thing we need to do too is wrap the model into a distributed data parallel object. So that's actually coming right here. So we need to import a distributed parallel from Torch parallel distributed and the distributed sampler. And basically what that object is going to do, I mean, it does quite a lot in the back, but it's going to make sure that the weights are synchronized across the processes when it starts. And then it's going to make sure that when you call backwards and the gradients are computed, they are going to be synchronized across all the processes. So as you go through multiple batches on each one of the processes, all your weights across all those replication stay in sync. That's what this distributed data parallel does. Then nothing changed on the optimizer schedulers. One small change here, we want to save the checkpoint only on rank 0. So here we can see that there is our first divergence within our processes. So only rank 0 is going to save the states. If not, it will override all the processes will basically override the checkpoint, and it will be unusable. And then finally, we need to tear down and destroy the progress group. So in Lightning side, the way it works is we just provide accelerator equal DDP. That's all. Like we just need to say accelerator equal DDP and provide TPUs equal Torch CUDA devices, which is the number of devices available on my machine. And now I'm basically training in distributed way with my Lightning code.
Yeah, and that's sorry. So that GPU's argument, that's just a number, right? You can set it 1, 2, 3, 4, whatever you want. Even if you have 8 GPUs, you can say 2 and it'll use 2. In this case, it's just a shortcut, so we don't have to hard code it. But I don't know. I mean, I already kind of forgot most of the steps from the previous thing, right? So I think that's one of the beauties of Lightning. It's like, I think people should do some of the stuff on their own for sure, for like learning purposes and to understand how things work. I mean, we do it, but we've been doing it for a long time. But a lot of what Lightning does is really just lets you get to work and do your thing. So you don't have to deal with like, wait, did I forget to zero out that process rank and make sure I didn't do this thing at that one thing. It's like, you just get it out of the box. It just works. It's very well tested, very scalable.
Yeah. Okay, so I'm going to show another one, and then I'm actually going to run the code to actually show how you do distributed training with pure PyTorch if you don't use Lightning. So, interesting. Okay, I'm not actually having the right path, so that's on me. Okay, so now let's say you use, so basically when you use distributed training with PyTorch, you have 2 ways to do. So the first one is DDP, which is used as DDP accelerator within PyTorch Lightning. And to do that, you need to have 2 terminals in which you are going to provide the word size, the local rank, and your script. So here we are going to run the script as many times as the size, as the word size. And then there's another option, which is spawning the processes. And the way it works is you provide a function, and MP spawn, which is relying on multiprocessing, is going to create multiple processing with that function. And you can also provide a way to communicate to those processes through like a queue or something, or you can provide parameters. So if you want to enable both of those in the same script, there is not much to do. You just need to add this uspawn here at the beginning, and there is like a small change to do on the setup part where you need to provide the rank and the word size, because spawn basically takes those 2. So that's actually what I'm going to run and show how that works in pure PyTorch, because I think if you have never seen it, it's a great thing to see. So here, when I'm actually going to run that script, we can see that 2 processes got registered. And here I'm actually running the spawn version of the code. So let's give it 1 sec, and we're going to see that now we are doing spawn distributed training. And in Lightning, that's basically called accelerated DDP spawn. So when you call DDP spawn within Lightning, that's basically what you get. You get the training with a multiprocessing spawn. The other way to train is this one. So here you can basically just do, and I think I had to add this parameter here to deactivate spawn. It's not just a bit of nothing special. So here I need to basically create my first process. So here I'm actually going to launch DDP. And here I need to provide rank 0. So basically every time I increment the rank, and I'm going to launch that. And here we can see registering rank 0. So here I have my first process, which has registered rank 1. Here I have rank 0, and training is going to start. Let's give it 1 sec. Yeah, awesome. So here we can see that on both terminals it's training, but in theory, we should see that the loss are different. So here I can see 236, like 233, and here I should see 299. And that's because the data which are being fetched are not the same on both processes. And that's the responsibility of the distributed sampler to make sure that those data are properly partitioned per processes. So I can actually go through my data faster and accumulate and synchronize the gradients. Okay, so I'm going to quickly kill those because they tend to, okay, awesome, it actually went pretty quickly. Any question at this stage?
Alan has a question. He's wondering if the data module works with image folders. Thanks, Alan, for your question.
Yeah, I mean, it's, as I said, it's basically just a component in which you organize your data loaders. So how you implement your data set, that's really up to you. Like, we don't enforce any constraints, that's really flexible. So if you want to implement your own image folder from Torch Vision, that's entirely fine. And you can actually find similar implementation actually in Lightning Flash, where we have the same structure, but for different type of data, so not only images, but also like potentially like videos, text, point clouds, graphs, and so on. But I will present that slightly later in the presentation. Okay, Will, do you want to add something?
No, go ahead.
Okay, so next, so this one is really quick. It's basically just accumulated grad batches. So if you wanted to basically accumulate gradients across multiple batches, the way to do is you provide accumulated grad batches to your train loop. And there will just be like those changes to do. So the only difference is instead of calling optimizer.step, and actually I forgot to remove this 0 grad here and make sure that it's under the same thing. But basically the idea is you call loss backward twice, and then you call optimizer.step. So actually here I have a small bug. But yeah, that's how it works. Basically, you take the batch ID, you make sure that it's being divisible by the accumulated grad batches, and that's when you perform the optimizer step.
But see, right there, that what just happened, right? So, I mean, we do this day in and day out for a long time. You will make a mistake at some point when you're adding new features to things, right? This is,
yeah.
If you try to add, accumulated plus distributed plus all this other stuff, suddenly your code is not going to be manageable, right? So yeah, that's the complexity that we're hiding for you.
Yeah, and I think like this one is actually a great example, right? Because I know how it works, but actually I messed up. I forgot to not 0 grad, which means now I'm basically not doing accumulation on one of the. So here I'm basically training on half of my data set instead of accumulating gradients over like every n batches, which is definitely not what I want. Okay, and then the last one I wanted to show is basically how you do profiling in PyTorch. So that's like a very exciting new feature which came out which has been updated through 1.7 and got like a lot of great improvements in the most recent releases. But the way it works is you import profile record, profile activity from Torch Profiler, and what you're going to do is create a context manager around your loop with the thing you want to record. So here I'm going to record like the CPU activities. I'm going to provide a schedule. So here I'm going just to profile on the first batches. And I'm going to provide an handler, which is going to say how I want those data to be saved. So how I want my traces to be saved. And here basically the way it works is we go through our batches, and every time we have seen the batches, we need to step the profiler, right? So that's a bit of code here, and as you go with more features, that start to be quite complicated. So here's the Lightning counterpart, right? So in Lightning, the only thing you will have to do is, so for the first one, accumulated code batches equal 2 here. So I'm doing accumulated gradient over 2 batches. But for the profiler, you just import from PyTorch Lightning profiler.pytorch, you import the profiler and the profiler activity, and you just pass it to the profiler. And that's exactly the equivalent as what's done here, plus the PyTorch profiler in Lightning does more things. He decorates the traces, adds record functions, which makes the entire trace easier to navigate. So that's what I wanted to show Alice here on how to implement those features and how Lightning make it extremely simple, right? So here we started by converting this pure PyTorch into Lightning. We basically saved almost 30 lines of code. And as we grow in terms of features, now we get like a 120 lines of difference between both our scripts, right? And the point is, as you keep growing and adding more features, it starts to be more complicated. And adding 4 features, it's actually not complex. Like what gets complex is like when you have 100 of them working all together and making sure everything works properly. And especially when you work with distributed training, because doing distributed training gets really hard when your processes actually diverges and you need to resynchronize them. And that's what Lightning does a pretty good job at. It's like when you train with Lightning, you get all those crazy things where you log and save only on when 0, but everything works and the states potentially get synchronized, but everything just works because we put the engineering work to make sure that when you use distributed training with Lightning, it can scale properly. So yeah,
something I think something that PyTorch users struggle with a lot is training on the cloud and doing it, especially on multi-node. If you ever tried this, this is a very hard thing to pull off. So I don't know, maybe you have something for us.
Yeah, I'm getting to that. I just want to like small quick notes here. So we got a couple of cool things within Lightning recently. So deep speed, fully sharded to basically scale trainings. We have multiple loggers, profilers. I already talked about that. We worked on something new, which is loop customization. And I really encourage the community to join Slack, contact us and say, I have this custom use case. I would like to have loop customization working for my own thing. So definitely ping the team and we'll be happy to work with you trying to solve those things. And then the next very exciting things, which is in the work, is fault tolerant training and the ability to restart exactly where it failed. And I think that's really important, especially when you get on preemptive instance in the cloud, which might actually save you quite a lot of money. So the bottle, like in a nutshell, basically, like if you wanted to implement all those crazy features in pure PyTorch, it's a huge number of codes. It's a lot of knowledge. And I mean, you can definitely give it a try, but that's definitely not something you want to do. And with Lightning, we keep it simple and we try to make sure that our API is as simple as possible so you can really focus on what matters. If you want to learn more, we have the Lightning docs right here. So there's lots of things to learn. And we also got some great new tutorials for everyone to learn about Lightning. So all of those are notebooks. There's actually an entire course which is being added right now. So everyone can go there and learn a state-of-the-art training way of using Lightning. Then we also released Lightning 1.4 yesterday. So that was a massive achievement from the community and from the team. So we have our changelog here. Have a look to all our latest changes.
Yeah, how many contributed to this release?
Yeah, I think we got like more than 60 contributors, which is I think one of the highest numbers. And yeah, actually like the entire list is right here.
Oh wow.
And we got like 450 squashed PRs for that release. So that's one of our biggest too.
And I think overall we have a contributor community of over 509 now, which is cool. So a lot of people really, and top labs, top PhDs, all that stuff, just dropping the knowledge in there.
Yeah, exactly. And if you want to take the release, you come here to the release and you will see 1.4, all the big highlights, TPU pod training, IPO accelerators, deep speed infinity, fully sharded, and so on. So here you have all the PRs, so you can basically like find breaking changes and really get updated to the latest of Lightning. At this stage, I'm just, if people have stars Lightning, feel free to do. It definitely helps a lot the community. Okay, so now I'm going to move to what Will teased, which is training on grid. So Lightning was really built to take care of all the engineering works for research, moving to production. And basically, Grid is an ML platform that has been built by the PyTorch Lightning team, which enables to train machine learning code without any code change, without worrying about the infrastructure, and really scaling if required. So here's how it works. So here you can actually go to, so here is actually the docs. Everything is available. And here's actually how it looks. So here I have my dashboard, and while working on this thing, I basically made 38 runs, spent like $13.
Yeah, and you can make an account for free, by the way. You'll get $25 in free credits as well.
Yeah. So if anyone wants to basically get this, so he wants to go inside of this this repo like Chaton PyTorch to Lightning and basically get those scripts to run on Grid. You just sign up, you get those $25 for free, and you can actually run those. So here, as I said, 38 runs for $30. So you can definitely get quite a lot done. So here's how it works. You just pip install Lightning Grid. The next phase is, so I'm going to actually do it just right there. So I'm going to take this script. It's not really different from the others. I just wanted to have it separated. So in the same way.
Can you zoom into the,
Yeah. Okay, so maybe I can just remove that. And okay, so basically, let's say I have this command right here, right, which is what I care about. And I'm going just to provide some extra parameters. So here I'm going to, so when you use the Lightning client, actually, one thing which I didn't say, okay, so actually it trains locally, which is great. So here you need to provide trainer max epoch GPUs, and here I'm going to train on 4 GPUs, right? So the way it works and how you train on Grid is basically you remove this Python at the beginning. And what you replace it for is basically Grid1. So Grid1 is the replacement for Python, basically. And the next part is you provide the instance type and the instance you want to run on. So you just do something like that, right? So, and what that's going to do is make a query to Grid, to the Grid platform, and basically schedule this new run. So that's going to take.
And so this model is going to train on 4 GPUs on one machine that has 4 M60s on it, right?
Yeah, exactly. And basically right now we can see we are using a G3 16 large. That's our script. And now if I basically refresh the runs part, so let's just rerun that section.
Yeah, and so again, you didn't change your code, right? So it was whatever code. You can try this on PyTorch examples, anything, doesn't matter. As long as your code supports multi-GPU, great. If it's Lightning, then automatically supports it.
Yeah, definitely. And here we can see like the, here's my code. And the cool thing is like everything has been gathered, right? So we know the GitHub repo, we know the GitHub hash, everything is entirely fully reproducible. And then once the run has actually completed, which is what you want, you can basically just copy the badge and give it to someone else so you can actually reproduce your code. And that's really important, I think, for the research right now, because I really hope we will get to a place where research papers will come with this kind of technology and people can basically easily reproduce those results and assert that what's actually written within the papers is what people claim.
And like I said, this is free, right? So you're not paying us anything for when you're in the community edition. You're just paying the AWS compute, right? So that's all you're paying for.
So one extra thing here, which I wanted to add is, so if people remember, in my data module, I was actually downloading the data right here. And that's something which can be painful if you have a big data set. So that's not something you want to do on Grid. What you will do is actually create what we call a data store. So a data store is a low latency auto version data set. So the way it works, Grid data store create, you provide the path to your data and you actually name it, and then you can add it to every run, so you can actually run on Grid. So to simplify that part, I actually created here in my data stores a means data set, so I actually uploaded those data, and then I made several runs. So here I have that example here where I just need to add data store minst and data store mondir. So here I'm mounting the data in the exact same way as I add them locally. And I think I did some runs where, so let's just check, not this one. So I'm just checking some of the runs I did today. Okay, so here we can see, for example, a successful run where I actually mounted the data. And here I can basically check, let's see if I can get the logs.
Yeah, and it seems silly with MNIST because it takes like 2 minutes to download, but this supports like 30 terabyte data sets, like really massive stuff that you really don't want to be messing around with when you're training on the cloud.
Yeah, exactly.
So does Grid support data versioning out of the box? Like the end user does not have to worry about.
Correct.
Yeah, and that's something which you can like handle if you want to. So
yeah.
Does it also have model versioning capabilities? Like, is it also easy to maintain version control for models?
Not yet, but everything that you see here, like this is fully reproducible, right? So the model that you just trained right now, you can always reproduce that exact same model like a year later because we have the code, the hash, everything, right? And the hardware.
Yes.
So it's 100% reproducible. So it is versioned, just not like how you would want it to be in like a Git type of way, right?
Right. The focus is more of model reproducibility and results reproducibility.
Yeah, and the data, everything, literally to the T, right? Because reproducibility needs everything. I mean, PyTorch takes care of a lot of the heavy work on reproducibility, which is like the seed and making sure ops work together. But then you need to go all the way to the hardware level and everything else to make sure something is 100% reproducible.
So guys, we are close to time, unfortunately. This is a very comprehensive and interesting topic, but I do want to keep some time for questions from the community.
Yeah.
Dennis has a question about torch metrics.
Yeah.
Are there plans to extend torch metrics with more, especially for COCO data sets? Thank you, Dennis, for your question.
Yeah, thanks a lot. Yeah, definitely. So I think the last patch, I might be wrong, was around adding support for audio, and I think implementation around object detection is really going to be coming in the next releases. So if you want to help us out, you can just get torch metric and push some of those metrics. That would definitely be very well appreciated. But that's definitely going to be a primary focus for torch metric, as we have the object detection task within Lightning Flash growing right now by the integration of Ice Vision and so on.
Yeah, don't be afraid to contribute. We help you, right? So if you have this implementation already, like bring it over to Torch Metrics. We'll help you figure out how to make it scalable, and then it'll be good to go after that.
Yeah, and if you do make a contribution, you can also like ping the team, and you will get like those cool swags, like a cool T-shirt and some cool things to stick out to you on your computer and everything.
Yeah. And I mean, we didn't get to it, but on Grid, you can also do multi-node, which was kind of the next thing. So if you want to train across dozens of machines, it's the same concept. You just change a number to like 32 GPUs and then off you go, right? So it's a very simple idea. There were questions around about data stores, I think I saw one. Sorry, the data modules. So data modules, again, like they're supposed to be really about reproducible things, right? Image folders, like Tomas said, whatever you want in there. It's just a black box, and you just stick in there anything. I think it even works with like NumPy and different things like that.
Yeah.
So,
Thomas and Will, you made some very compelling points on why anyone should be adopting PyTorch Lightning. And typically, we want to stray away from comparisons with other libraries. But if you had to let the community know specifically why when should they be looking at PyTorch Lightning, or for what use cases is PyTorch Lightning most optimized for? What would you say?
Yeah, it's really around professional use cases for research and production, right? So if you already know PyTorch, you know what you're doing, and you want to scale it up, but you want to focus on like the business problem or the science that you're trying to solve, then Lightning is for you. If you don't know PyTorch, you should learn basics of it, because Lightning is not a new framework. It's just organizing your PyTorch code. So if you don't know PyTorch, you're gonna have a hard time, right? So we're not really meant. It's not try to automate all this stuff for you. So that would be I think the main one. And like this is, I think one of the fastest growing machine learning libraries today, very well tested across many companies and research labs. Many papers published on this as well. So if you're ever wondering like, am I going to get bottlenecked? This is going to be, like we all got burned by this at some point. We converted to some framework, and then like 6 months in, we were like, oh shoot, I'm blocked. I can't do anything, right? That's not going to happen here, because we've designed it specifically for that not to happen.
Yeah, and what I will add on that is, I mean, first I started to learn deep learning with like FastAI, so definitely a big fan of the framework. But what I would advise people to do is just quickly go through the repos, so like FastAI, Ignite, and Lightning. Like quickly look at the examples, and what seems the most intuitive for you should be like maybe the framework you should choose, because like at the end you are going to work with that framework like quite a lot of hours. So you want to work with something which is easy to understand and easy to modify and like adapt for your own use cases.
Yeah, that will add. I think like again, many great frameworks out there. It's really going to be your personal choice. We have a lot of dedicated effort into Lightning. I mean, we're a company as well, so we have a lot of engineers focused on it full time. A lot of contributors as well. So we put a lot of resources behind it. So it's not going to be. Everything we do is going to be very, very well like tested and robust.
That's great. So we usually end these episodes with a question that sometimes is a curveball for some of our guests, but I expect it might be easy for you. What is the one feature that you would like to see in PyTorch core?
Well, there's so many, but for a long time, I really wanted complex tensors, and you guys delivered on that, so that was great. That like literally, it blocked me in my research back in the day. Someone did bring up XLA. I have to say, I think XLA was probably the thing that everyone's been asking about the most, getting that to work with TPUs. But there is an issue where if the ops drop into CPU, it's like really hard to tell when that happens. And then we get complained at all the time because people are like, why is Lightning so slow on TPUs? And we're like, guys, it's just like, you have a knob that's not supported. It's not us, right? So yeah, I think we can't do the warnings. I'm pretty sure we can't do the warnings. I think that has to be done at the core level, but that would be useful. Yeah. I mean, that's me. That's my wish list, I guess. Tama probably has his own.
Yeah, I mean, I have one which is along the line of Will. I think like the new work around sharding is really interesting. And one thing which I would like to see is potentially support from deep speed or fair scale for TPUs, because there will definitely be a lot of scaling there. And I think sharding is definitely the future as we grow model size and we grow data sets. So getting like this support across all the different hardwares and platforms will be quite neat, because I'm sure like a lot of people will find use cases for them.
Yeah, without giving away too much, I can say pretty confidently that this is not something that's not going to be in PyTorch for too long.
Maybe I should flip the question to you now. What would you like to see in Lightning?
In Lightning?
What is one thing you'd like to see in Lightning? And it's okay if you guess something we already have, then that's better, right?
The one thing that I've been challenged with is trying to deploy it on multi-clusters. And the fact that Lightning makes it so easy is, for me, the most compelling reason to use Lightning.
Yeah, there you go. I mean, that's something we definitely support. Slurm, Torch Elastic, all that stuff. And again, if you're using cloud providers and your stuff's public, like Grid is free, try it out, and like that is going to do multi-node on the cloud like very trivially, right? So you don't have to deal with it. and we support spot instances, which is cool.
Yeah,
so,
and it's actually quite robust because we are actually going to migrate Lightning CI multi-nodes to Grid directly, so we can actually like test out Lightning with like Torch Elastic at scale and so on.
All right. Wow, this was great. Thank you for the very comprehensive presentation and for answering all of our questions. It was really great having you guys on today. And viewers, thank you for joining us today on this episode. If you still have any questions, please feel free to drop them in the comments, and we'll have William and Thomas reply to those comments on under the video. So even if you're not able to watch this live, but maybe you're in a different time zone, maybe you're asleep right now, please post in your questions and we will have them answered. Thank you for joining us today. And do subscribe to the channel to get notifications about our next stream. Until then, we'll see you.
Yeah, bye everyone. Have a pleasure.
Thank you for having us. Bye.